7, 6, 5.
Hello, and thank you all for coming. VWPPE is off to a grand start, and we will continue our Beyond the Stage momentum with our next keynote speaker. We are fortunate to have such a distinguished international group of keynotes and presenters. Michael is a researcher and instructor in the Department of Media Architecture at Future University in Hakote, Japan. He has been involved in educational technology design, implementation, research, and consultancy for over 15 years, working closely with higher education institutes, schools, and media companies in UK, Singapore, Malaysia, and Japan. He was awarded the second prize in the United States Army 2012 Federal Virtual Worlds Challenge for his research. Please help me welcome this afternoon's keynote speaker, Michael Vallance. Michael, the floor is yours.
Okay, thank you very much, Letty. It's very kind of you. Just want to double check that everything is fine and everybody can see me and hear me. So, looks like. Okay, I'm going to... Okay, great. So, good morning. It's early morning here in Japan, so I'm going to wish you all a good morning, 5:36, but a beautiful day by the looks of it. So let me get started with my presentation, and I'm going to joggle between the speakeasy transcript and my slides, so please bear with me. So my name in world is David Beresford, also known as Michael Vallance in the real world. I'm in the Department of Media Architecture right up in northern Japan at Future University, Hakodate. And I'm going to show you how we use robots and virtual worlds to collaborate across the world between Japan and two schools in South Wales in the United Kingdom. Of course, I'd like to acknowledge my co-researchers, Catherine of University of South Wales and Stuart of Hull University in the north of England. Of course, the teachers and students at both Mountain Ash and Aberdare high schools in South Wales. My own students, of course, and the wonderful metaverse designers at FireSaber and Reaction Grid. And I'll come to talk about those a bit later. So I hope you find this presentation interesting. I'll try to take any questions at the end. So let's move on to the next slide. So I hope to show you how we use virtual world simulations to support something what we call robot-mediated interactions. Now, we started this project back in 2009, and the long-term aim of this research is to try to design what we call an evidence-based framework of learning, one undertaking tasks of a measurable complexity in a 3D virtual world. And basically, how do we do that? Well, one, we capture students' procedural processes as they work through task solutions. And I'll show you some examples of this a bit later. We capture their learning reflections during and after completion of tasks. And we then collate the data as students collaborate in world when programming a robot. And the tasks that we undertake, we consider a successful task consists of a robot and program solution to solve very specified circuit challenges. Now, in this presentation, the focus is on the development of measuring complexity of tasks involved in these robot-mediated interactions. So let me move to the next slide. So what's the context and the current motivation for our context? Now, I think this is quite interesting because on March the 11th, 2011, the large earthquake and tsunami badly damaged the cooling system reactors at the Fukushima nuclear power plant here in Japan. And we know that 4 reactors exploded and that radioactivity was released to the atmosphere. And yet in December 2011, the reactors were declared stable, and I'll put that in inverted commas, but there are still problems. And the problems that currently are many evacuees simply cannot return home anymore. The Japanese government has changed its criteria for dangerous levels of radioactivity. Basically, they increased the criteria. And workers are still struggling to maintain the safety of the plant. Now, I've got references to these at the end of this presentation from the IEEE. And unfortunately, deformities are being discovered in local wildlife. But this is not publicized in the international media, but just go to Greenpeace and you can see the evidence there. So this really is our motivation. But one of the most surprising related episodes was the lack of robots in Japan to assist with the recovery operations. Less than a week after the tsunami, iRobot USA donated 2 of its Packpot and Warrior robots to the nuclear plant. USA engineers trained the Japanese operators the following week, and yet it took 3 weeks for TEPCO, the nuclear power company, to authorize the use of the robots within the reactor. So, I don't want to get into the pros and cons of nuclear power, but as educators, what can we learn from this disaster? Basically, we believe that people need to be better informed and equipped to make sense of the vast amount of information, and that collaboration is essential communication for now and for the future. And the tasks in this research aim to support 1 and 2. Now let's look at our research, which involves communicating in the virtual world to program robots, the Lego Mindstones robots. Now, in a nutshell, the students' aim is to communicate solutions to problems which involve programming robots to follow specified circuits. Now, this is undertaken by designing circuits which necessitate the use of robot maneuvers and sensors, and experiencing collaboration in this virtual world with students in Japan and the UK. Now, it's reasoned that these experiences lead to some personal strategies for teamwork, planning, organizing, applying, analyzing, creating, and reflection. Let's move on to the next slide. Now, we found in our previous research that there's no generalizable mechanism in the discipline of robotics or human-robot interaction for accurately measuring task complexity. And this was quite surprising. And when we looked at the literature review of task complexity involving robots, to reaffirm, there appears to be no consensus about what makes a robot task complex. So, how one task can be compared to another one in the domain of robots remains still a little bit of a mystery. However, given the specific purposes of the use of our robots in the research, in 2010, we used the work of Barker and Ansorge and Olson and Goodrich, where task complexity was calculated according to the number of sections that made up given mazes. And we thought, okay, we can work with that. And we call this circuit task complexity. Now, in this slide, you can see an example of circuit task complexity. The number of directions, the number of maneuvers, the number of sensors, and the number of obstacles basically can be measured. Now, we presented this particular metric at last year's conference, and we've written about it in some papers we've had published. Okay, next slide. Now, from our tasks in 2011 and 2012, we actually found this to be inadequate. We found that over a period of our research, as the circuit became more complex, so did the programming, of course. The students actually started to use a lot more sensors. However, simply adding more sensors to the circuit task complexity formula was inadequate because the programming required for sensors to move over a bridge, for example, is far more complex than the programming required for sensors to move around obstacles. So imagine a Lego robot moving over a bridge, imagine a Lego robot moving around obstacles. They both use sensors, they both have the same circuit task complexity number, but they're actually more complex within the formula itself. So we needed to modify the formula. Let's take a look. We decided to look at the student solution. And we looked at the different programming objects within the Lego Mindstorm software itself. And what you can see in front of you there is a snapshot of the graphical user interface Lego program. And the number of variables within each of the objects or within that program. And we considered that the variables can actually correlate to the number of decisions required of the student with each Lego next program block when actually developing their program. And we thought that was a reasonable assumption to make. So we correlated the programming variables and the objects to design a new formula which we call now robot task complexity. Now on this slide you can see the robot task complexity formula being applied to our previous problem. We think it's fairly straightforward. The student's next program solution consists of 8 blocks, 3 sensors and 3 loops, and each has a fixed variable. Simply adding this data to our robot task complexity formula derives a single value, which then we can use as a measure of student solution complexity and maybe a little bit later, possibly student performance once we linked all the other data that we've collated. Of course, we appreciate that this formula can only apply to the Lego Mindstorms program, but at least now we have something that we can analyze in terms of the circuit task complexity problem against the robot task complexity solution. And as a side, we also use other software called LabVIEW when we're trying to look at how we can apply a similar formula to that as well. But that's for another day. Okay, let's have a look at how we implement these tasks. Now, students in one country are provided with a task specification. The students then work on a solution. They then construct a circuit in the real world, in the lab, and also in the virtual world lab. And they develop the Lego Next program to maneuver that physical Lego robot. The problem and proposed solution are then later communicated in real time to students in the other country via the virtual world. So one task with other students in England, in Wales, developing the solution. And then once they've done that, they would then communicate to the students in Japan their solution and teach the students in Japan. And that would, the next task then would be repeated Japan to UK. Okay, next slide. The task specifications that we have robot actions, they have the circuit task complexity, the collaboration, anticipated STEM, which is important for the schools, essential skills, and the robot task complexity. Obviously, we can't put that in until after the students have finished the task. Now, many of their criteria, it's agreed that they are anticipated, but at least it provides a focus for the researchers and the teachers, and also the students. Now, it's also important to have comparable resources. So let's take a quick aside now and look at some of the resources that we use in both the university in Japan and the 2 schools in the UK. We've agreed to use the Lego Mindstorm software. We have the same kit, what we call 8527, which is the basic Lego robot kit. We have similar blocks. You can see in one of the pictures we've got those huge Lego blocks. We have those in the university and the two schools. And we all have the same Apple hardware and operating system. We all have the same 15-inch MacBook Pros, We all use Snow Leopard OS X, and we don't do any updates. We make sure that everybody's got the same hardware, software, and the only difference is the internet connection. Now, the students construct different circuits in the real world, and you can see in this picture an example of a circuit, and you can see the robot, you can see the obstacle, you can see the path, maybe the challenge, the target. Okay, we have some beautiful robots that have been constructed over the last 18 months by our students. Number of different designs since September 2011, using sensors, using the basic kit. Okay, and we have, and we even have what we call a so-called real robot from RobotSim, and this was donated from National Instruments for us, and we actually got that for those distractors, often my colleagues, who think that Lego robots are simply toys. Yes, they are, and no, they aren't. They're very powerful robots, are our Lego Mindstorms. But for some roboticists, it's a toy. So we actually got, we actually replicated some of our tasks using that very large robot sim, simply to demonstrate to our computer science and robot colleagues. It distracted us from our real research, but we felt it was important to communicate to the computer science people that what we're doing is of value to computer science students, as well as from an educational perspective as well, considering all our students are between 17 and 19 years of age in both schools and the university. I just wanted to get that in. Okay. So the students have constructed a number of different challenges from the specifications that we provided. And examples have included, follow the line, going over obstacles, going around obstacles, and many others. And here's some pictures of some of the circuits there. Now, our first place of communication is our new Aurora Sim, OpenSim virtual space hosted by Firesaver. The students meet up in real time in the virtual world, usually 6 p.m. Japan, 9 a.m. UK, but that's fine. We've scheduled it as such. We have customizable presentation boards. We have video streaming on a prim, and also the students can control our real-world robot from the UK, and I'll talk about that a bit later. But it's important to note that a lot of these tools were developed and decided by the students in a very iterative manner. So the students construct their problem and a circuit solution within the virtual world. Of course, we use voice, but actually, it's amazing that students prefer to use text chat, and they say it gives them time to think about what to say. And one would imagine that would have been the Japanese students, but actually it wasn't. Surprisingly, this comment was made by the students in the UK. Of course, students in Japan were happy about that, but even though I use students in Japan, and of course the students in the UK are both fluent communicating in English, they both teams like the text chatting. So, okay, that's better for me because then I can collect the data, the transcript directly. Okay. Now, on this slide, you can see some of the tools that we've used that have been developed by our students within the virtual world. I'm sure they might be familiar to people who use Second Life often, but I just wanted to display it for you. Okay, and these are our students engaged in some of the tasks, and you can see some are building bridges, some are programming. The essential thing is it's teamwork and collaboration, and they're having fun. That's very important. Okay, and the same goes for this slide here. Okay, where am I up to? And what's important is to note that students have never programmed robots prior to this project. We like using beginner students on this project, which is why I use first and second years in Japan, and the students in the UK are sixth formers, first year doing a baccalaureate. So they'd be 16, 17. You can see that they quickly developed different robots to follow the line and drive wall obstacles, throw balls, and then one of them actually throw balls like a baseball to knock down some paper cups. Just fun activities, but the programming behind it is just terrific. And like I say, everything is communicated via the virtual world. No cheating through Skype or email. Nope, it's all through the virtual world. Okay, and then the resulting programs, and therefore the robot task complexity, as you can see from this slide, become quite complex. For those who know LEGO Mindstorms robots, may see that this is a fairly decent program to develop for a beginner programming student. Now, we've also conducted some of our robot tasks inside a virtual Fukushima. Remember that the context for this was the Fukushima tsunami and earthquake at the nuclear power plant. And this is hosted by Reaction Grid, and we're using Unity 3D software. Okay, and there's a slide there of the work in development, shall we say. And what's also fantastic is that the students now in I say England, but South Wales, UK, can now control quite smoothly our LEGO robot in the Japanese lab with a time lag of about 1 second and a video feedback lag of about 2 to 3 seconds via the Bambusa app, a bit like Ustream. Essentially what the students are doing in the UK is that they can log in and using the controls within the virtual world, within OpenSim, they can actually control our physical LEGO robot in the Japanese lab. And, well, this slide shows that, and we like to call that telerobotics for the rest of us. In other words, it can be done. You don't need to have a PhD in robotics to do this. So that's another task that we undertake from time to time, is the telerobotic controlling. Okay, now what does all this mean? Well, for the simulations, we have a flow chart in addition to the task specifications. That's important to communicate to the teachers in the schools, what we're doing, where we're going, why we're doing it. Okay, and of course we have the task specifications, and now let's take a look at some of the results that we've garnered from 28 tasks of various specifications from September 2011 through to February 2013. For each task, we measured the circuit task complexity. We looked at the program solutions, so we could calculate the robot task complexity. And then we actually recalculated all the complexity values between 0 and 1 by basically dividing each of the task value by the maximum possible value. Again, there's not a lot of mathematics goes into that, but it's one way of measuring the problem and the solution. What we could then do is compare the circuit task complexity problem against the robot task complexity solution over the 28 tasks. And if you look at this graph, we can actually see some correlation between the circuit task complexity and the robot task complexity, as shown by the peaks and valleys within this graph. And this graph actually should be anticipated because it represents really the expected level of complexity given by the teacher and the student's achievement. That is the robot task complexity. Ideally, the teacher should provide a task commensurate with expected successful outcome to be developed by the learners. Any task, I guess. But of course, there are differences, and we can measure that difference. And the difference we've actually called something that we call task fidelity. Now, task fidelity is calculated by simply subtracting the robot task complexity from the circuit task complexity. And then we can plot the task fidelity against the order of increasing challenge as determined by the students. Now, how do they determine that? I'll come to that a bit later. And ideally, the task fidelity should be 0. The tasks above the 0 line indicate that the teacher's task was higher than the student's solution value. In other words, the task was difficult or that the students did not meet the anticipated solution. The tasks below the 0 line indicate the student's solutions exceeded the teacher's expected task complexity. We found that tasks T2, 4, 5, 10, and 20 all have one factor in common. These tasks necessitate the use of sensors. Students found tasks which involve sensors to be more difficult. Of course, students were also more anxious during these tasks, as we'll see later from the immersion data. Task T10 and T28 had small task fidelity values, so these would be considered the ideal tasks of the 28 undertaken. These also involve the use of sensors, but both of these tasks are where students from the UK were teaching students in Japan. And I'll come back to this in a later slide quite soon. So let's look, how did we determine how immersed the students were within each task? So to do that, we asked them about the challenge and skills during and after all their tasks. Now, in earlier work, we had what we call a virtual iPad would appear in front of the avatar, where 2 questions appeared, and the avatar itself was forced to answer those questions to make that iPad disappear. And the wonderful thing about that was that the data then was automatically transferred to our database online. However, it actually proved quite unreliable, and we got it timed to pop up every 3 minutes, but it sometimes it did, sometimes it didn't, and that was a problem because we really needed to capture students' thoughts during the process of the activities and the tasks. So we actually now resorted to pen and paper until we get a technical solution to this. But it's important that we capture the immersion data of the students. And to do that, we correlated then what we call the skill and challenge, and we divided the sum of these scores by all students and divided it into the total maximum possible score for each task. For example, 4 students would have a maximum of 16 for skill and 16 for challenge, and we took a calculation that we could then graph, as you can see on this particular slide. Again, the values are between 1 and 0 for comparative purposes. This comes from research by Pierce et al., which is referenced on the last slide of this presentation, and it's an indicator of immersivity, what he called flow, which I'm sure many of you are familiar with. The optimal line of immersivity of flow is shown on this graph, and we have boredom and anxiety indicated at the 2 corners of the graph. And we found that tasks T10, 12, 18, and 21 were considered tasks of optimal immersivity given the data from the students that we captured during and after the tasks. And that's all the students. And these particular tasks involved robots scooping up items and chopping items. So the robot itself was rather complex, but it was actually doing something which was considered quite fun. One of them was to scoop up, I think it was scooping up different balls, and the other one was chopping up virtual fruit, and then chopping up some plastic fruit that we call in Japan suikawari, chopping watermelons. And that was an interesting robot. And I've got a link to a video of that again at the end of this presentation, if you want to have a look. So if we look at the data of task fidelity and immersivity, we actually suggest that task T10 and T28 would be considered the most successful tasks, where students are engaged in what we call robot-mediated interactions. The task fidelity value for T28 was only plus 0.08, slightly above the optimal task fidelity line and slightly below the optimal immersivity line. Similarly for task 10, with immersivity slightly above the optimal path and task fidelity at plus 0.01. So even though the sensors were used in the tasks, and even though students' data revealed they found sensory tasks difficult, actually being immersed in a task with sensors led to some student success. And that might be the key, is attempting to get students immersed in tasks. Another observation here is that the UK students were better teachers than my Japanese students. And I actually suggest this is more to do with cultural communication strategies than English fluency, because my students are good enough at English, of course the UK students are, and it's more to do with the cultural fluency. And for people who are doing international collaboration, this is a very important factor. So the challenge for us now, and for teachers, is to try to seek tasks similar to T28 and T10, where immersivity is close to or on the optimal path of immersivity, and the task complexity is close to or on the optimal line of task fidelity. Another challenge is to seek ways to transfer these observations to other tasks with different participants. Of course, that's what research is supposed to do, and that's what we are going to do from September. Now, in order, the reason the challenge is to seek ways to transfer these observations to further tasks in order to develop more reliable, optimal learning tasks when the students are engaged in these robot-mediated interactions. Well, to sum up then, the applied research, we're attempting to develop some metrics for recognizing learning when engaged in collaborative virtual world tasks. The motivation of this implementation was the nuclear disaster of 3/11. We've built a virtual Fukushima nuclear plant. We've got the Aurora OpenSim training space that has been iteratively designed and continuously built. We've got international collaboration by students as non-experts. They've highlighted the benefits and challenges when engaged in constructing these robot-mediated interactions within the context of distance-based communication inside virtual 3D spaces. We have something called students' immersion or flow, circuit task complexity, and robot task complexity. And these have been calculated. And we have some optimal learning tasks that we've highlighted. And we have a new metric for measuring tasks involving robots, which we like to call task fidelity. I got some links, which I will put in the text chat there. And these will take you to Robots in Actions, a video of the project. We've got an app you can download, which just promotes our project. And we've even got an answer to our roboticists showing how our real robot also works, quite similar to the Lego robot. And that really ends my presentation, and I'll be happy to answer any questions if I can. And there's a list of the references that I mentioned throughout this presentation. So thank you very much.
Thank you very much, Michael. If anybody has any questions, please type them in text chat, and Michael will entertain them for you, and he will read them out.
Okay. Somebody said this is very important work. Thank you very much. We think it is too. Okay, one question was, did the kids need fluency in LSL? I guess LSL, you mean Second Life. The answer to that question is, we use OpenSim, and the answer is yes. There's a steep learning curve using virtual worlds. I can't just take it to a class and use it with students. Usually it takes at least 2 or 3 tasks to get the students comfortable working in world and then become immersed. We've been using the same students for 18 months. From September we'll have new students. We'll be doing the same again. Somebody suggested LSL is scripting language. Actually, we have 1 or 2 students will do some scripting. We try not to get too involved with the scripting. We got great support from Reaction Grid. We have great support from FireSaber for the 2 different spaces. We're using a FireSaber Aurora Sim more at the moment. But I have one particular student who's interested in scripting, and he can do some scripting. I have another student interested in Unity 3D. That's his summer project.
Michael, I believe somebody had asked also if your slides would be available somewhere.
Well, yes, they will. The website I have, and I think there's a link maybe in my abstract, at that blog, I'll put a link into SlideShare, and I'll upload these slides to SlideShare, and I'll put that link in the next 30 minutes after this talk. Okay, somebody suggested then the time zones being a problem. Yes, but luckily working with the 2 schools, they actually have set up the time for their project class at 9 a.m. on Thursday, which is 6 p.m. in Japan. So for my students at 6 p.m. is not a problem. For the school students, the school has actually scheduled the class so that it fits with this project. We meet once a month for the tasks, the collaboration. The other 3 weeks, students in Japan, students in the UK are independently working on their problem solution and practicing. And it's a great project because the students in the UK, it's part of their baccalaureate project. One question was, are there any standout problems you find meeting in world? Mostly the problems are technical. The time we've sorted out, the connectivity, sometimes with the internet in the UK side, because it's a school, the technicians have to bypass the routers set up at the school when we do these tasks. If our wonderful technicians are not around, it could be a problem, but so far, so good. When they meet in world, there is the desire sometimes for the students to say, can we go into Skype? Can I send this solution by email? And we explain that's actually not part of the research. Yes, you can, but that's not part of the research. However, there are easier ways of collaborating, easier ways of communicating, but we actually want to work in virtual worlds because we want to, push the boundaries of what students can do in a virtual world. In addition to that, the idea of setting it up as a simulation so the students are controlling the robots from within the virtual world is a reason for not using Skype. It's a reason for not using email. It's a reason for not using a web browser. Using a virtual world, we're actually controlling the robots. We can visualize the robots in a simulation, and then they can transfer that to the real world. By doing this over and over again, we're learning what are the benefits of a 3D virtual world. So it does take a little bit of convincing to the students, because they want to find, of course, the path of least resistance, which is often Skype. Okay, I'm just reading a question. Okay, somebody looks like they asked me a question, but I've got so much text in front of me now and I can't find it. Where is it at? Okay, in short, what's your backup plan? Do you know, the backup plan would be Skype, because it's important that the teachers, especially in the UK, that when they do a task, they've actually got to make sure that the task is undertaken in some shape or form. But we've never actually had to resort to Skype. We've found that the students, that the OpenSim space itself is not a problem. The students can communicate. The biggest problem is basically ensuring the internet connection. And you know, even if we use Skype, even Skype is blocked in schools, and the technician would have to be there to bypass the router in the school, even for Skype. So we say Skype is our backup plan, but if the internet cannot be accessed from the school for any particular reason, the technician's off sick or something, then we'll just have to cancel that particular that task and rearrange it. But we've never, if we got access to the internet, we've never had a problem using OpenSim. Okay, one person said, I was a teacher at high school in Japan for 20 years. Can you tell me the profile of Japanese students? Yeah, sure. At Fuji University, these students are very techie students. They study media and they study computer science or programming. The students on my project are handpicked because they are smart students. They are conversant in English because that's important for the international collaboration. And maybe they're a bit different from the regular students. They're much more open-minded, they're much more relaxed, they're much more creative. They're, like I say, they're 18, 19, all male. That's mainly because it's a mostly male student population. Yeah, and they're nice. They're very amenable students. Another question is, will they work at a computer company? Most likely. Previous students from previous research used in 2009, the students there have all gone on to work for computer companies, either as systems engineers or as programmers. And not the big companies either. They've gone to the smaller companies, which they chose themselves. Another question is, are you using the Jive platform for multi-user applications when using Unity? The answer to that is yes. That's our second project with another group of students, and that we consider that work in development. We've got a virtual Fukushima set up using Unity 3D in Jive, hosted by Reaction Grid. And we hope to develop that alongside our OpenSim Aurora Sim space. Another comment was, I'm sure there must be a grant to fund this. Yes and no. Yes, I had a grant over 2 years from both the UK, what's called the Prime Minister's Initiative, and that served us very well. And I had a grant from the Japanese government for 2 years, and that served us very well. And I invested. I got the spaces built, the virtual spaces set up and hosted and paid for. I bought the technology, the laptops, the server access. I'm on a fiber optic line. I bought a stack of Lego kits and sent them to the UK. The schools in the UK get no money, so I basically kitted them out. But now that that fund is finished, I'm applying for additional funds. I was not successful this year, but my university is very supportive. And they give me funds to continue this project. I pay my students, but it's nothing like the previous funds for setting it all up. But I kind of anticipated that. So I bought a lot of technology 2 years ago. There's nothing wrong with the technology 2 years ago. Another question is, have you convinced the school with your results that this is worth the effort? Absolutely, yes. The two schools in the UK love this project. It's got terrific support from the physics teacher, from the design and design and technology teacher. They're not regular schools. They're doing the baccalaureate, which is slightly different from the regular schools. The headmasters there are very supportive. And from tomorrow, I'm actually flying to the UK, and I'll be going to the schools next week to meet up with the teachers who are still there before they go on their summer holidays. Very supportive, and my university is very supportive. I must say, I wish I could get the Japanese government to be more supportive and give me more grant money, but that's another issue.
Any other questions for Michael?
Yeah, somebody commented they see the kids are learning, and that alone is a reason to support and fund the research. Thank you so much, and I totally agree. And I'm trying to get out there. Why I give presentations like this is I want to show so many people the wonderful work that, not what I'm doing, it's what the students do. And just watching the students work together is just wonderful. And it's actually wonderful watching the students in the UK communicating with the students in Japan. Remember, I'm in the north of Japan. It's not Tokyo, it's not Osaka, it's right up in the north. They don't get to meet that many non-Japanese youngsters up here. So it's great for them. So thank you all very much.
Thank you all very much for coming and listening to Michael's very fascinating research on robotics. We appreciate, please acknowledge his efforts. Thank you all very much for coming. We do have a few more exciting presentations today. We have some workshops, we have some panels. I hope you all can join us for the party at the end. And then hopefully we'll see you again tomorrow. Thank you all very much for coming. Michael, thank you very much for keynoting today.
Okay, thank you all very much. Have a nice day.